I'll try to not interrupt this time. I'm so sorry for that. Let's finish this. Okay, then paper continues to blocking or grouping. Quantization precision is in part determined by whether all quantization bins are equally used. Sorry, all quantization bins are used equally. Okay. For example, a 4-bit data type has 16 bins, but if on average only 8 bins are used, it is equivalent to a 3-bit data type. Okay. As such, methods that help to increase the average use of all quantization bins in the data type can increase quantization precision. Yeah, it can. In the subsection, we introduce blocking or grouping methods, chunk the tensors into smaller pieces and quantize each block independently. Uh-huh. Tensor, you this helps to confine outliers to particular blocks, which increases the average number of bins used across other blocks and thus increases the average quantization precision. Let's see in appendix if they have this explained anywhere. Dequantize. But they have this pretty clear, I guess. At least the introduction or a point direction to go through if we want to learn about quantization more. But I'm not going to delve into that now. So blocking or grouping. Blocking and grouping are similar concepts. In grouping, we subdivide a tensor along a certain dimension into n parts and assign each subtensor called group in its own normalization constant, okay, which is usually the absolute maximum of the group. In blocking, we view the tensor as a one-dimensional sequence of values and divide this sequence into parts of size n called blocks. Okay. Blocking is basically you take the tensor in one dimension and split it into blocks. Grouping, you take a tensor and uh, divide it along a certain dimension. It can be two-dimensional tensor and dimension tensor, but you make n subtensors. You make n blocks. In our work, we use blocking because, unlike grouping, it provides a measure of additional bits per parameter, independent of the hidden dimension. The paper also mentions the advantages of blocking or blocking and grouping and why they use blocking to leverage uh, measure of. For example, 60-bit normalization constants and a block size of 64 means we have an extra 16 bits every 64 parameters, or 16 by 64 2.25 bit per parameter additional cost for using block-wise quantization. This is true for every model regardless of hidden dimension. For grouping, the extra cost would depend on the size of the hidden dimension of the model. For blockwise quantization, we use the notation of Detmers, which defines the blockwise quantization with k bits, block size b, and input tensor t. Blockwise quantization with k bits with n elements n by v blocks as follows. If QMap maps the integer representation of a data type to the representative floating point value, for example, a bit representation of a 32-bit float to its real value, and if we define the index of each block in 0 to n by b, by index b, we compute the normalization constant as mb max of tb. Then blockwise quantization can be defined by finding the minimum distance to the value of the quantization map as follows. Minimum distance of the argument is the blockwise quantization. Okay, outlier dependent quantization through proxy quantization. So outlier features that emerge in large language models can cause large quantization errors and severe performance degradation. While it has been shown that it is sufficient to use 16-bit inputs and 8-bit weights to avoid this disruption, it is unclear if outlier features can cause degradation if we use 16-bit inputs and weights below 8-bit precision. To end this, we develop outlier dependent quantization through proxy quantization, where we quantize weights into higher precision for the corresponding outlier feature dimensions to test how much precision is needed for the weights. A significant challenge is that each model has a different number of outlier features, and outliers particularly depend on inputs that are different from each zero-shot task. As such, we seek a model independent model that has a constant memory footprint across all models and tasks. Proxy quantization, which is basically they call this, what is proxy quantization? We read that. We read that. Yeah. In initial experiments, we noted that the criterion developed by Detmers, which thresholds the hidden states to detect outlier features, is unreliable as it depends on the standard deviation of the hidden state. This causes problems because for models such as OPT, the standard deviation of the hidden states increases in later layers, which causes too many outliers to be detected. This also has been noted by Zeng et al. Okay, by inspecting this anomaly in OPT models, we find that a better measure of detecting outlier dimensions is the standard deviation of the weights of each hidden unit of the previous layer. The standard deviation of hidden unit weights that produce outliers are up to 20% larger, 20 times larger than the standard deviation of other dimensions. We provide further data as a correlation analysis of the relationship between standard deviation and the outlier size. With this insight, we develop what we call proxy quantization. Proxy quantization is input independent and therefore task independent, as it uses standard deviation of each layer's hidden unit weights as a proxy for which dimensions have outlier features. For example, given a transformer with n layers, linear layers, with weight matrices Wi, where h is the input dimension and o is output dimension. We define the set of indices j to be quantized in higher precision by so and so, where standard deviation output dimension o, we then quantize the input dimensions of the weight of the next layer in 16-bit if this is in set j and k bit otherwise. The paper developed a outlier dependent quantization through what they call proxy quantization, which uses standard deviation of the weights of each hidden unit of the previous layer to measure or detect. This method is input dependent, hence model independent, and can be used for their comparisons across all the tasks, models, in the context of the experiments. Okay, we are near. So experiment setup. In our experiments, we use 16-bit inputs and k-bit quantized parameters for 3 to 8 inclusively. What? Yeah. Mm, less than or equal to. Right? No? Yeah, 16 bits at all. Yeah, okay, whatever. Maybe this is right. 3 to 8 16-bit inputs. Attention matrices are not quantized since they do not contain parameters. We also use the 16-bit baseline that does not use any quantization. To measure inference performance for k-bit quantization methods, we use perplexity on the common crawl subset of the pile and mean zero shot performance on the ALM evaluation harness. In particular, for the zero shot setting, we use the Ether ALM eval harness, and in the GP2 setting, task lambda, okay, health swag. The choice of this particular zero shot task was mainly motivated by previous work of Detmers et al. And Shaw. Okay. However, in our evaluation, we find that the perplexity is a superior metric since its continuous value per sample leads to less noisy evaluations. This has also been noted by Franter et al. For example, when using perplexity to evaluate data types, quantile quantization is the best data type. Still, when we use zero shot accuracy as an evaluation metric, the float data type is sometimes better because zero shot accuracy is nicer. Furthermore, we find across more than 3,000, 35,000 zero shot experiments correlation coefficient between. Okay, this highlights that the porosity is sufficient and preferable for evaluation purposes. And serious drawback is that is challenging to interpret. As such, we use zero-shot accuracies in the main paper for the clarity, but encourage the reader to use perplexity measures found in the appendix for replication and comparison purposes. Since perplexity evaluations are so reliable, it is possible to replicate our work by evaluating a small number of samples using the perplexity metric, which makes the construction of scaling laws less computationally intensive. The paper also set the details of experiments to be able to write any replications, and they used uh, perplexity as a main evaluation metric because metric uh, and short accuracies for clarity, but they encourage the use of perplexity for comparison, even though it's challenging to interpret because of the this intensive uh, to come that I can fight to fit power loss to our data, but we find that bivariate power function with respect to the number of parameters and the bit precision provide a poor fit. However, when we fit linear interpolations to represent scaling curves, we find that different bit precisions are almost parallel, indicating that the scaling trends of different precisions can be represented faithfully by a base function and an offset for each bit precision. As such, we linear interpolations choose to use interpolations to represent scaling trends. What's the results? Bit level inference scaling laws. The main results are shown in the figure 2. Where is that? Oh, oh, what is here? This episode the zero shot accuracy over general number of bits for 3 to 6 MB parameters. We make the following observations. For given zero step performance, 4D precision needs optimal scaling for almost all the model families, and the only exception is bloom where it's better slightly, but not significantly better. Scaling curves are almost parallel, which indicates that bit level scaling is mostly independent of the scale. An exception to this is 3-bit quantization. Pythia and OPT are unstable for 3-bit inference, where performance is close to random, 35% for the largest Pythia or OPT models. The experiments led to the following observations. They observed that they observed that for any given zero shot performance, the 4-bit sum gives the optimal scaling for all the almost all scales, families, and scales. Scaling curves being parallel indicate that bit level scaling is mostly independent of scale, and 3-bit quantization is exception for the above results. It performed uh, performance performance is unstable and close to random models like OPT. Given the main scaling results in improving scaling laws. Given the main scaling results in figure 2, an important follow-up question is how we can improve the scaling times further. To end this, we run more than 35,000 zero shot experiments to vary many of the recently stated advances in quantization precision, including the underlying data types, quantization block size, and outlier dependent quantization. These methods usually improve the quantization at a small cost of additional bits. For example, a block size, no scaling improvements for 6 to 8 bit precision. We combine all possible combinations of quantization methods with 6 to 8 bit quantization, and we find that none of these improve bit level scaling. It appears for that 6 to 8 bit precision, the model parameters have enough precision to not cause any significant performance degradation compared to 16-bit weights. As such, scaling behavior can only be improved by using less than 6-bit precision, rather than enhancing the quantization precision through other means. Small box size improves scaling. Um, they also gave lot of insights on which uh, what factors can degrade or improve scaling. Okay, the rate will be read. Recommendations and further work. For recommendations, by default use 4-bit. use a block size of 128 or row to stabilize 4-bit quantization and improve zero-shot performance. Uses floating point or a quantile quantization data type. In some cases, integer data types might be preferable to improve inference latency depending on the implementation and hardware support. A case where higher bit synthesizable is one works with the GPU with enough memory to hold a higher bit precision but not a larger model. Fine precision, half it, full precision. So this is highlight the form. Action is to focus on low bit precision below 4 bit. Scale drives. And blocking is better performance than 0 shot 3 bit float. So basically, these are all the probable directions you can take with this research. Let's see if there are any limitations. Okay, 3,500 experiment, 35,000 experiment. Why am I saying 3,500 experiments? 35,000 experiments. A main limitation is that we did not consider certain classes of quantization methods. For example, there are quantization methods that where a data type is optimized with additional input data or from the weights of the model alone. Optimization from the weights alone is similar to quantile quantization, which was the most effective data type in our study. As such, this hints that such quantization methods could improve scaling for inference and present a missed opportunity to be included in our study. However, a study is an essential step towards recognizing the importance of these methods for optimizing the model-based accuracy trade-off, a perspective that did not exist before. And the limitation is the lack of optimized GPU implementations. It is unclear if other data types that rely on lookup tables can achieve significant speedups. However, efficient implementations of a int or float data types would be possible, and our results for other data types can still be useful for development of future data types. Only study the latency optimal perspective indirectly through studying the model-based accuracy trade-off. The practical limitation of the latency optimal perspective is the low-bit models with 16-bit inputs might be less latency if model is applied. Okay. Final limitation is loading the weight matrix is only part of inference latency, which needs to be optimized to achieve fast inference. Attention. The large chunk of inference latency footprint. Um, some of the limitations of the study are missed quantization classes that they were not able to generalize for all the models or tasks considered. Then uh, uh, there might be better GPU accelerate optimized data type implementations that would reduce the latencies by a larger scale. LLMs. Okay. So basically, that's it. This is very interesting paper, and thanks for sticking through. And yeah, I'll try to do more of this in more interesting ways, not as boring as these. Sorry and thank you. Bye.